Hello guys, happy Halloween. Sorry I couldn't be here. You'll have to eat lots of candy for me in my place. So today you will need the lesson 18 notes, lesson 18 assignment. Those are over in the basket and next to the basket. You'll need a pencil, colored pens or highlighters would be fine, and a straight edge. So we're going to go ahead and get started. Remember that this video is uploaded to Student View, so if you find that you had a hard time keeping up with the lesson today, then you can rewatch it when you get home and get a better understanding, or rewind to whatever part you need to. But keep in mind that you will need to rewatch it, or you can rewatch it if you need to. So just keep that in mind. To begin with, our essential question is, how is the definition of an isosceles triangle helpful in a geometric proof? Today is Thursday, the 31st, as you all know. So you can pause that if you need to write that essential question, but I'm going to go ahead and get started. So our opening exercise is to describe any additional piece of information needed for each pair of triangles to satisfy the SAS triangle congruence. So we started our SAS last class, and so now I want to see what information I would need to know, additional information. So given, I can see that AB is equal to RS, so this segment, if you are highlighting or you're using a colored pen or whatever the case is, you could color code this AB, and that AB corresponds to this RS. And what I would probably do for that is also put one little mark through them. So I would say that this piece here is congruent to this piece because of the given. I don't know why I did that. Okay, so that's this part. We also know that AB is parallel to RS, so I could notate that as well. So them being parallel would mean that I could put an arrow through here and an arrow through here. And really, I'm trying to prove that triangle ABC is the same size or congruent to triangle RST. So the two triangles that I'm looking at, ABC being this one, and I'm trying to see or to justify that that triangle is actually the same size as RST, so this one here. Okay, so now I know what I'm comparing, I know what I'm looking at. The parallel lines give me some additional information. So the fact that these are parallel means that if I thought back on those parallel lines and transversals, these two parallel lines have a transversal cutting through them, and that transversal being this segment here. So from C to S. So if I looked at C to S as my transversal, I should be able to easily now identify that this angle that's formed with the parallel line in the transversal is congruent to this other angle here formed by the parallel line in the transversal, and it's because those are corresponding angles. So going back to this, I don't need to know that. That's not additional information needed because that I could infer based on those parallel lines. So the last part, I would say, if I looked at my yellow triangle, I have a side labeled right here, and I have the angle, but I would need to know something about this other side, so the two sides that form that angle, because remember, that's what I'm looking for SAS. So I would have to say that additional information I would need to know that CB is congruent to another segment on the green triangle, and so that segment on the green triangle would be, this is T, so I would say that since I know this side, and I know this angle, the other side I would need to know is from T to S. I would need to know that that is congruent to this CB. So if I knew that, then I could say this information plus those angles plus the lines that were given, that's enough for me to say that those triangles are congruent to each other by SAS. Congruence. So again, a lot of you guys, I think, are good at identifying what SAS should look like. Now we're going to put reasons to it to say, well, I would need to know this, or I know this because of the corresponding angles, that kind of thing. So today we'll talk a lot more, today's lesson is very proof heavy, so we're going to put this SAS to use a little bit, and hopefully it'll make a little bit more sense to some of us. So today we examine a geometry fact, and actually I should have had you get a compass. Sorry. Let's go back and change that. You will also need a compass, so if you need to pause this to grab a compass, you can do that. I'm going to switch it so that my next class that watches it knows. So you will need a compass. So going on to this next exercise, it says we will examine a geometry fact that we already accept to be true, but we're going to prove this fact in two different ways. So we're going to use transformations and we're going to use SAS congruence criteria. So in this space below, let's take a minute and construct a triangle ABC. So an isosceles triangle ABC. So how would I do that? I'm going to start by taking my straight edge and just drawing a small segment here. Then I'm going to take my compass, and normally if I was doing an equilateral triangle, I would measure this length of my segment and then use that as my radius. But since I want an isosceles triangle, I'm going to make this a little bit longer. So I'm going to move this and make an arc up top. And notice the radius I used was just something bigger than my original piece. So whatever you decide to use is fine. But then you're going to keep that radius, and I'm going to move my compass over to the other end of my segment. Same radius though, and then I'm going to make an arc up top. So now I can say that if I took my straight edge and connected that intersection to my endpoints, I would have an isosceles triangle, and that's what I wanted. So here is an isosceles triangle ABC. We accept that an isosceles triangle, which has at least two congruent sides, like it does here. So maybe let's call this A, and then we'll call this B and C. So two congruent sides in our case is AB is congruent to AC. Also has, so I know that isosceles triangles have two congruent sides, but I should also know that they have two congruent angles. And so in this case, those two congruent angles are angle B down at the bottom, because that's across from one of my congruent sides, and then angle C down at the bottom, because it's also across. So I'm going to say angle B is congruent to angle C. So we already know that this is true. Now we're going to take a minute to prove that this is true, because before I just told you, hey, just so you guys know, this is the property, these are the properties of isosceles triangles. So now we're going to take a minute to prove that. So again, if you would draw another isosceles triangle just down below here, we're going to do our first proof by transformations. So if I drew just a small segment and did the same thing that I did earlier, took my compass, placed it there, I'm going to change my radius so it's just bigger, any size, and then I'll make my arc, move my compass over, make my arc, and then I will connect those endpoints to that intersection. And again, I'm going to label this top angle as A, and then I'll do the left as B and the right as C. So to start my proof, it says, given we have an isosceles triangle, boom, here it is, with AB equal to AC, boom, boom, we already did that. I'm going to prove that angles B and C are actually equal to each other. So I can construct an isosceles triangle, which we already did. Now it says to draw the angle bisector of, I'm going to say let's do angle A, where D is the intersection of the bisector and the segment BC down at the bottom. So now we have to think back on how to construct an angle bisector. So hopefully you have not forgotten that. So I'm going to place my compass on that angle that I'm trying to bisect. I'm going to set my radius, it doesn't matter what size, but I'm going to do it to where when I make my arc, it intersects the angle at two different spots. So I've got an intersection here and an intersection here. Then I'm going to take my compass and move it down to one of those intersections, and I will draw another arc. Then I'll move my compass to the other intersection, draw my other arc. And so now I can connect the vertex of my angle, so connect A to that intersection. And so of course mine isn't going to work with me. There we go. So when I draw that bisector, that's what I get, but I'm going to extend it all the way down because I said that I want D to be the intersection of that bisector and BC. So this is going to be my point D. Next it says that we're going to let R be the reflection through AD, so I'm reflecting across AD where the reflection of B ends up. So if I looked at this, I'm going to reflect it over to this side. So I'm going to place my compass here, take my pencil onto that other side. I'm going to switch colors so that it's easy to see. If I were to make my arc, notice again I have one intersection here, one intersection down at the bottom. So I'm going to place my compass there and draw an arc. Place my compass on the other intersection and then draw an arc. And you'll notice by doing this, my B prime would end up right here where the C is at, right? So here, the reflection of B ends up where C is currently at. Using similar reasoning, we could reflect C over, but we know C prime would end up right over here just by looking at that same reasoning. So C would end up over where B is at. So knowing that, that means that if I took this whole angle and I reflected it over, then this whole angle would reflect over to this side. And that justifies that this triangle had two equal sides and it had two equal base angles. So my construction justified that for me. So that would be a proof by construction, which we typically don't do, but I figured it was worth remembering all of those different things. We did a bisector, we did a reflection, we did all kinds of stuff here. So next, I'm going to write a proof, just a regular proof. So using my SAS, so the new stuff we learned last class. So it says, given an isosceles triangle ABC with AB equal to AC, that's already labeled. Again, I'm going to try to prove those base angles are equal. It says to draw the bisector AD, so similar to what we did up here. So I'm going to take the angle bisector, so I'm going to draw my first arc, and then I'm going to draw this next arc, move it over, this next arc, and then I'll draw my line straight down from A to this side. And I'm going to call this D again. So the reason I'm doing that is because anytime I use SAS, I should have two triangles that I'm comparing to each other. So now, before I started with just one triangle, now I've split it down the middle, so I've got two of them. So D is the intersection of the bisector and BC, just like we had before. We're going to use this as an auxiliary line to help us get to SAS congruence. So now, since I'm writing a two-column proof, I'm going to go through and draw my two columns. So I'm going to start by saying that my statements and my reasons, right? Let me type that out instead. And again, you can pause this if we need to, or just rewatch it at home. So my first statement is always my given. So isosceles, let me make this a little bit smaller. We're doing an isosceles triangle ABC. And we're saying that AB equals AC. And my reason is given. So my next thing is trying to identify SAS. So looking at these two triangles, I can already see that they have a side shared. So this side, the given part, that's already a side that they have in common. So the next thing I could say is, looking at it, they have this overlapping side. So for example, this yellow triangle on the left, if I'm comparing it to, say, the green triangle on the right, they both overlap there at AD. So I'm going to use AD from the yellow triangle and say that it's equal or congruent to the AD from the green triangle. And I'm just going to use equal since I'm typing. It's easier to do than the congruent symbol. If it helps, you can color code. So you can say AD from the yellow one was equal to the AD from the green one. Also here, AC was on my green triangle. It was this side. And then AB was from my yellow triangle. So we've got two pairs of sides already labeled. My reason for that being true, anytime something equals itself, that's the reflexive property. And then I can draw my next line. The next thing we did, notice that to get that auxiliary line that I had, I actually bisected this angle. So I'm going to say construction of angle bisector, because I constructed that angle bisector to get my auxiliary line. And that construction really meant that I bisected that angle. So I created two angles that are equal to each other. So now I can actually go through and say, well, because of this construction, because of this construction that I did, this angle to the left is equal to this angle to the right because I made it that way, right? So now I'm going to say over here that the angle BAD, so this top angle here, is congruent to, and I'm just going to draw in that congruent symbol, so is congruent to the angle over here, CAD, and that just so happens to be that way because I constructed the bisector. Again, if you're color coding, you could note that BAD was the one in the yellow triangle, and then CAD was the one in the green triangle. Now going back and comparing the two triangles to each other, this triangle on the left has this side, this angle, and this side. And the triangle on the green has that similar combination, side, angle, side. So now I could just go forth and say that triangle BAD is congruent to triangle CAD. And my reason would be SAS congruence. But that's not really what I was trying to prove. I was trying to prove that B and C are equal. So now that I know that the triangles are congruent, I can say, well, if the triangles are congruent, that means every single part of the triangle is congruent. So that must mean that this angle B down here is congruent to this angle C. And my reason for that, hopefully you remember, I don't know because it's been a while, was that CPCTC, I think we've said this before, I might be making this up, but CPCTC is corresponding parts of congruent triangles are congruent. Oh my gosh, sorry. So since I know that those triangles are congruent, that means that all of their corresponding parts are also congruent. So this angle B corresponds to the angle C because they are the first angles I named there, right? So that would be the end of my proof. All right. So I want you to keep in mind that you can only use this CPCTC after you've proven that two triangles are congruent. And so far, the only way we've determined that two triangles are congruent is by using this SAS congruence. So next week, we'll start to talk about different types of congruencies. But either way, CPCTC comes after two triangles have already been proven to be congruent here. So you'll see that in my next set of proofs. So go ahead and flip over to the back. Here we start with a new triangle, a new proof. So I'm going to start with my statements and reasons. And so now again, I want to label what's given to me. I want to type out what's given to me, etc. So given, I know that JK is equal to JL. And I know that JR bisects KL. So those are the two things that I'm going to start with. So I'll write them in my proof first, and then I'll go through and label stuff. So knowing that JK and JL are equal, I would put a little mark through them. So JK, JL. JR bisects KL. So this bisects should tell me something. So bisect really means that it's cutting something in two equal parts. So if JR is bisecting KL, that means this KL is being split up into two equal parts. So I'm going to say for my next part of my proof that I actually use the definition of a segment bisector to determine that KR is equal to RL. And that's really what I drew in my picture there. So now that I drew it, I'm going to put it into my proof. So those two are equal because by definition, bisect means to cut into two equal pieces, right? I need to think about what I'm trying to prove now. So I'm proving that JR, remember this symbol means perpendicular, so this means forms a 90-degree angle. So now I need to think, how could I justify that there's a 90-degree angle in there? So I've got these two pieces of information. The next thing I would say is look at the fact that this JKL is an isosceles triangle, and I know that because it's got two sides that are equal in measure. So I'm going to make that claim here. I'm going to say that triangle JKL is isosceles. And I'm going to say that by definition of isosceles. So by definition, an isosceles triangle has at least two sides that are congruent. And in this case, that is exactly what I have. So now that I've justified in my proof that this is isosceles, I also know that there are some base angles that are equal. So I could say that the angle across from this side, so this angle here, angle JKL, is congruent to the other one that's across from this side, so JLK, right over here. And my reason I knew that those were equal was because they are base angles of an isosceles triangle. So base angles of isosceles triangles are equal in measure. So I've got that in there. Now again, notice that I've got two triangles in here that I can compare to each other. So this triangle on the left, JKR, has a side, an angle, and a side on it. And if I look at this triangle on the right, it also has a side, an angle, and a side. So I can say that triangle JKR is congruent to JLR. Keep in mind those orders of letters matter. So triangle JKR is congruent to triangle JLR. Notice that I could tell the order of letters based on what corresponds to what, right? So I know that this K should correspond to L. Those are both the middle letters, right? I know that JK, since I listed them first, should correspond to the side that it's equal to, JL. So I would list JL first. So hopefully we have not forgotten that. So I would say that that is true. My reason would be because they meet SAS congruence criteria. Or you could just say SAS congruence. After that, you can say, well, I'm trying to really prove that JR and KL are perpendicular. So I'm trying to prove that this line forms a 90 degree with this line, right? So to do that, I'm now going to say, this is where we get a little crazy. I'm going to say that I don't know the measures of those two yet, but I could say that this angle here, if I added it to this one, would form a linear pair because they form that straight line. So I'm going to say that the measure of angle JRK plus the measure of angle JRL equals 180. And then I'm going to say my reason is linear pair. But I did also say in the last problem that once you prove two triangles are congruent, you can use that CPCTC. So I could also say that since those are congruent, notice that this angle R from the triangle on the left corresponds to the angle R from the triangle on the right, because they're the two last letters. So I'm also going to say that angle JRK is congruent to angle JRL because they correspond to each other. So now that I know that they correspond to each other, I'm just going to label them exactly the same way, right? So I'm going to say if that has two arcs, then this one will also have two arcs. Now, we're almost finished, which is good because I am almost out of room. If those two are equal to each other, then I'm going to say, and actually I'm going to change the way that I wrote this. So I'm going to say the measure of JRK is equal to the measure of JRL. And so the reason I would do that is because now I can take this and I can substitute it in to this place, right? Because I know that that's equal to JRL. So I'm going to write my new equation out. I'm going to say that the measure of JRK plus substituting that in here would give me another JRK equals 180. And my reason is substitution. Now you'll notice that I have two JRKs. I'm going to have to finish my proof over here in this space. So if I combine like terms, I could then say that I have two measured JRKs that equal 180. And my reason is combine like terms. Notice I could take this and divide both sides by 2 now. So if I divided both sides by 2, I would end up with the measure of JRK equals 90 degrees, because 180 divided by 2. My reason, since I divided, would be division. Property. And that's really what I wanted to prove. I wanted to prove that that was 90 degrees because that would prove to me that those are perpendicular. So finally, now that I know that that's actually a 90-degree angle, we could put a little box in there to say that's 90 degrees. I could finish off my proof and say, okay, now that I've proven that's 90 degrees, I can then justify that JR is perpendicular to KL, and that would be by definition of perpendicular lines. So sorry that we ran out of space there. That was kind of a lengthy proof. This whole lesson is kind of a lot of lengthy proofs. So we will see how far we get with it, and then you can watch the video at home again if you need to. So going on to the next one. Again, I'm going to start off by writing my T-chart, statements, reasons. I would say write kind of small because this is going to be kind of lengthy too, or you can get out a separate sheet of paper if you want to just straight up do it on a separate one. So statements, reasons. Again, I always want to start with what is given to me first. So I'm given that AB equals AC and that XB equals XC. And then we will draw our line. Since I'm given that information, I'm going to go ahead and label it in my two triangles. So AB, this side is congruent to AC. XB and XC, so XB, XC. And then now think, well, what am I trying to prove? I'm trying to prove that AX bisects BAC. So AX bisects this angle BAC. So in order to prove that that's a bisector, I need to somehow prove that this angle to the left is equal to this angle to the right. So that's really what I'm trying to do. So what I would do is, we have two congruent sides, two pairs of congruent sides. So if you think about this triangle here, for example, that's an isosceles triangle. So knowing that's isosceles should tell me that these two angles are equal to each other. So I'm going to start with that. I'm going to say that the measure of angle XBC is equal to the measure of angle XCB. Notice the different order of letters. So XBC is the one on the left, XCB is the one on the right. And those are equal to each other by definite or base angles. They're base angles of isosceles triangles. I also know that there's another isosceles triangle. So if I were to look at, say, the big triangle ABC, right? Then on the big triangle, I also know that this whole angle is equal to this whole angle. So I'm going to write that out. The measure of angle ABC is equal to the measure of angle ACB. And that would be for the same reason, because that's a big isosceles triangle. So you can highlight that if you want to, but you don't have to. So since I know that the big angle is equal to the big angle and this little part is equal to this little part, that must mean that this other little part would have to be equal to each other, right? But I need to prove that. So I'm going to say that the measure of ABX, that would be this angle here, that little angle is really equal to the big one minus this small pink one. So I'm going to take that and write it that way. So ABX is really equal to the measure of ABC minus this small one in here, which was XBC. And I'm going to do a similar thing to this right-hand side. So I'm going to say that this angle here, A to C to X, and that's really equal to this big blue angle ACB minus the small one underneath, XCB. Ugh, I messed that one up. Okay, XCB. And so this one is kind of like angle addition, except I did angle addition and then I subtracted on both sides. So if you think about angle addition would be adding two small angles to get a big one. This one I'm saying, well, if I would have added those and then subtracted on both sides, this is the equation I'd end up with. So I'm going to, just to shorten this proof, because I know it's going to be long already, I'm going to say for my reason that this is angle addition postulate and subtraction property. So I kind of combined those. If you have questions on that, I'll clarify that on Monday. But I really did just a combination of those two. So the reason I did that is I'm really just trying to prove that these two angles are equal to each other, because if I have that, then this triangle up here has side, angle, side again, and this one will have side, angle, side again. So I want to prove that those two angles are equal, because I already know that the sides themselves are equal. So looking at this, I know that ACB is equal to ABC, so I'm going to rewrite this equation, but I'm going to substitute in it instead. So I'm going to say that the measure of ACX, instead of ACB, I'm going to plug in this other thing it's equal to, so ABC. And then instead of XCB, I know XCB is equal to XBC, so I'm going to substitute that one in too. So my reason for that is two substitutions. And then now we notice, wait a minute, this equation equals ABC and XBC, and this equation equals ABC and XBC. So my next thing is that I have two equations here. I have this one and this one that actually equal the same thing. So I can set them equal to each other. ABX equals ACX. When two things equal the same thing like that, I would use the transitive property. And now, hey, I have proven kind of what I wanted. So I'm going to come back and erase this part. And I'm going to say, well, this had an arc and a line through it, so I'm going to put an arc and a line through that because I just proved in my proof that those are two equal angles, which is great for me because now I can say that this yellow triangle to the left with its SAS matches up with this triangle on the right because it also has the same SAS combination, SAS. So my next statement is going to say that those triangles are congruent. So ABX, triangle ABX, equals, or sorry, not equals, is congruent to triangle ACX. Again, this is by using SAS congruence. But again, that's not quite what I wanted to prove. That'll get me there, but really I'm trying to prove that AX bisects. So now that I've proven that the yellow and green triangle are the same size, right? This one being the green one, this one being the yellow one, they're congruent because of SAS. Now I can say that their corresponding parts are congruent. So I can use that CPCTC to say the corresponding part that I want. So to prove that this is a bisector, I want to prove that those two angles are equal to each other. So now I can say that easily. So I can say that this angle, maybe two lines like that, right? So angle BAX is congruent to angle CAX, and that's because they correspond to each other. So you can imagine if you folded the green triangle over onto the yellow one, those two would be the same size, so they correspond, right? So, okay, now I've justified that those are equal in measure. By definition, if those two angles are equal in measure, that must mean that AX is an actual bisector. So I'm going to jump to what I wanted to prove. AX bisects angle BAC, and my reason is by definition of angle bisector. So knowing that I created two equal angles meant that that must be a bisector by definition. Okay, we're almost finished. Oh my gosh, I've been talking your ear off. I'm so sorry. This one, let's see how long. It shouldn't be too long, but I will try to shorten it the best I can. So given, let's start off with that. Let me scroll down. Okay. So again, start off with your statements and reasons, write in your given information. So my given information is Jx equals Jy, and that Kx is equal to Ly. And then I'm trying to prove that I have an isosceles triangle in here somewhere. So again, let's start by labeling what we know to be true. So Jx is this piece, and then it's congruent to Jy. I know Kx is this small piece, and that's equal to Ly. And I'm trying to prove that JKL, this big one, is isosceles. So looking at this, I can tell just by glancing that this triangle JXY is isosceles because it's got two congruent sides. So that tells me that angle 1 and angle 2 equal each other. So I'm going to say that the measure of angle 1 is equal to the measure of angle 2. My reason is because they are base angles of an isosceles triangle. Maybe let's just draw a triangle for that so I don't take up too much room. Okay. After looking at those two, notice that I have two other triangles that I could compare. So if I look here on the left, I have this triangle JXK, and that triangle has a side and another side labeled. So if I can somehow prove that this 3 is equal to this other angle 4, then I could say that those triangles are congruent because of SAS, right? So I want to try to get there. So in order to do that, I don't know anything about angle 3 yet, other than if I added angle 3 and angle 1 together, they would add up to 180. Those are a linear pair. So my next reason I'm going to use is linear pair. So my linear pair, I'm going to say that the measure of angle 3 plus the measure of angle 1 equals 180. But I could use that logic over here. I could say that the measure of angle 2 plus the measure of angle 4 also equals 180 for the same reason. So both of those are sets of linear pairs. I also know from earlier that 1 and 2 are equal to each other. So if I took this one and rewrote it, I would say that the measure of angle 1 plus the measure of angle 4 is equal to 180. My reason for that would be substitution. Notice now I have two equations that equal 180. So I know I'm going kind of quick here, but I know that you're probably tired too. So this equation equals 180 and this one equals 180. So I'm going to use those and the transitive property to set them equal to each other. So now my equation is going to say that 1 and 3 equals 1 and 4. And notice that you have angle 1s on both sides, so I could subtract them out. So subtraction property would leave me, if I subtracted angle 1, it would leave me with the measure of angle 3 equals the measure of angle 4, which is perfect because I wanted to prove that those two were equal to each other, and now I have. So now I can jump to say that those two yellow triangles are congruent. So triangle JXK is congruent to triangle JYL because of SAS congruence. If those are congruent, that must mean that their corresponding parts are congruent, so I can use CPCTC. Corresponding parts of congruent triangles are congruent. And I can say that the corresponding parts that I care about that would make this an isosceles triangle would be proving that this is congruent to this. And looking at my order of letters, JK are these outside letters, and JL are also the outside letters, so they do in fact correspond. So JK is equal to JL because of CPCTC. And now that I've proven that those are equal, now I can say easily that that big triangle is isosceles. So I'm going to jump to say that JKL is isosceles by definition of what an isosceles triangle is. And that's it. You guys survived my big, long lesson. Sorry that I couldn't be here today to teach it to you myself. I find that proofs are usually easier when I'm around so I can answer questions, but you know, it is what it is. So take a look at this. Again, please, please, please rewatch it and pause it and go slowly if you need to go slowly and see what I did where. You do really need to understand proofs. So we've seen them before. Here they are again. Please, please rewatch this at home if you feel like you're not very comfortable with it. Your assignment today is proofs. Try your best on them. I did leave an answer key with a sub, so if you need it, you can ask some clarifying questions. I will, of course, answer questions when I see you guys again next class, but please give it a shot. Try it yourself and see what you can come up with. We can always write the proofs together if you need it, but yeah, hopefully it made sense. I hope you guys have a happy Halloween, and I will see you when I see you. Okay, bye.